Okay, so it's 5 p.m. now. Let's see, we have 13 people here, not bad. So first thing first, can everyone see this text clearly? Okay, and one thing that I would say in the front is, well, first, welcome. And then second is that I know this teaching experience or learning experience is really weird because you guys are watching a video and then paying full tuition. And if I'm a parent, I would not like to do that. But on the other hand, if you can see what I'm seeing right now, it's actually worse. Okay, because I'm in my basement talking to an empty room and supposedly do this for an hour and repeat 40 times this semester, and then it's completely silent, right? Because all of you are muting your microphone, so it's completely silent. And then I have a camera that's like it's actually 10 feet away from me so that we won't get the distortion of this whiteboard. And to see your face, I have another screen, right below the whiteboard in front of me to see you guys, see the face of you guys. And from what I experienced last semester, talking in an empty room, usually your energy level goes right down. Okay, so usually last semester what I did is I pre-record all the classes and then post it on YouTube. And when I did that, I actually record video like every 10 or 15 minute section and then recombine them in post. The reason is that if it's completely silent, then you start to wonder what you're doing, in this empty room. And then and you start to question yourself, okay, why am I here? And it doesn't feel good. And I tried it, it doesn't feel good. So this is just a personal request, okay? If you guys want the best teaching experience, if you want your instructor to feel energetic all the time, turn on your camera. It's not that I don't want to. It's not that I want to see you. It's just I want to know that there's someone here in the room. Otherwise, it's kind of weird. And then the second thing is that the entire purpose of doing this live, okay, doing this live is actually kind of difficult because Zoom has kind of a bandwidth limit. So I actually have a separate recorder from my camera to record everything. So the entire point of doing this on live is that I want to make sure that the student instructor, we can ask question and answer question in real time, because this is what we are learning is quantum mechanics, and this will be different from any class you've ever learned, and this will be very different. So if you don't have the chance to ask questions, then I'm almost like 80% sure that most of you wouldn't be able to understand the content of this class. And then the other thing is that some of you might type in the chat, but then I'm not able to see that because my computer is actually 10 feet away next to the camera, so that's how I stream this video. Okay, so if you have questions, don't type in the chat, just speak it out, okay? So that's the first thing. And then the second thing is that I'm required by the university to ask you guys, is there any objection that we're recording this video? This is kind of ridiculous, right? We're remote, we have to record, but I'm required to ask you guys these questions. If there's any objection, please raise your hand or whatever. Yeah. And the second thing is that, is it okay if we post the recording of this video on YouTube? The reason for that is that YouTube is actually the best viewing platform for video, let's be honest, right? It's much better than whatever UVA platform we're establishing here. It saves a lot of bandwidth and then it compresses the video really good. If you guys are okay with that, then I will post the video on YouTube next day. And then normally I don't see anyone else watching the video because I'm not a YouTuber, right? So I don't have any other followers. So and also required by the university, okay, when you guys ask questions, never say your last name, okay? If you say your last name, I have to edit it out because I'm not allowed to post anything that contains your full name, okay? So it's kind of ridiculous, but that's how it is. And I don't want to get fired because of doing, teaching a class, okay? So any suggestion for this online format? I mean, you guys probably taken a lot of online classes last semesters. If you see any faculty doing a better format, please let me know, send me an email. I think I have a lot of gear that I can play with to adapt to their format. Okay, so oh, I forgot to introduce my name. My name is Xu Yi. Okay, I've heard probably more than 10 different pronunciations, so you can't surprise me. Just pronounce the way that you want, and I won't be offended. And in fact, my PhD advisor, tried 6 years, and then he still couldn't pronounce it the correct way. Okay, so that's perfectly fine. And then the third thing that we're going to talk about today is the grade. Okay. I'm not sure what will happen this semester, but my guess is that eventually it will be pass or fail. Okay, because online learning is not fair to the student, right? Some of you might have better connections, some of you have better learning environment at your home. So for the grade, just to make it very easy for you guys, the homework would be 60%. Okay, and then homework 60%, midterm will be 20%, and then final would be 20%. Okay, so if you do your homework and then you attend the exam, okay, I doubt whether you can get 0 because that's challenging, to get an absolute 0 in any exam. Then you will pass. Okay, it's as simple as that. Do the homework and then attend the exam, you will pass. And in the previous 2 years, we actually give flexibility of the format of the final exam. Okay, you can do a mini project and you can do a presentation. This year, we still offer the same option. Okay, but then I'm not really encouraging you guys to do that because by the end of the semester, it's very likely that you will return to your home. And I'm not sure how you guys can work remotely on a project together. Okay, but if you really want to do that, it's okay. Okay, so for example, in 2019 fall, 2 groups of students did a presentation on the quantum supremacy paper from Google. Okay, so it's a 30-minute presentation on the hardcore what the paper is about, not the not the like BS. It's actually a hardcore presentation, and 4 of them get an A from that. And you guys can do that this year as well if you want to. But from my personal experience, or from what they told me, it's actually much easier. The final exam is actually much easier than the project. Okay, so for the homework, so because we're doing this remotely, is there any suggestion how to submit the homework? Previously, I just asked students to send it to me by email, but then last semester I only have 5 students doing homework. So do you guys have any suggestion? Like I heard a lot about Gradescope, right? Is that what you guys are using? You can do this or this. Okay, so Gradescope. Okay, I would learn that. We have a week before I send out the first homework set. Okay, so this is homework, and then textbook. The textbook, recommended textbook, is already included in the syllabus, and then the one that I really recommend you guys to get is the Griffith, Introduction to Quantum Mechanics. And the way to use that book is to, treat it as a tool book, right? If you want to know, okay, if you don't remember what equation is what, and then you can look up in that book. But if you want to learn quantum mechanics from that book, it's almost impossible. Okay, I don't know if any of you have that book in front of you, but if you actually open it, I haven't read it for the past year. I think it's either on the first page or second page. They actually give you the Schrodinger equation. Okay, out of nowhere, give you the Schrodinger equation and tell you to absolutely believe in them. Okay, so that's not the ideal way that we teach. Okay, so we will not see Schrodinger equation until the 4th week, and by that time you will actually be able to derive Schrodinger equation. Okay, so that's the textbook, Introduction to Quantum Mechanics. I think it's $25 on Amazon. Okay, and then class notes. So is someone asking a question? Okay, anyway, yeah, if you have questions, just speak out. So for the class notes, whatever I have in my hand, I will send out to you guys. I will post it on UVA Collab, right? So you don't have to take notes, and also because whatever I write down here, you will find it on YouTube, right? So there's actually no reason to take notes. So you can actually focus on what we talk about in class, and then really ask questions. Okay, if you don't understand something, just ask. Okay. And well, the final thing is, I would say, one more thing is that the class roster is actually made available on the UVA Collab. The reason for that is that, well, because you guys are not in classroom, so you don't know who's actually in the class. So, but in this class, I encourage you guys to find at least one, one friend with you to work together on the homework, or even form a little bit of study group. The reason is that often when you look at a homework set, the first reaction is, what is this, right? What is this? And having a second person or third person or have a group working on it will really help. And then you can just ask the person sitting next to you, right? So right now, go on the class website and then see who's there. And let's see, how many people do we have here? Do you guys want to do an introduction of yourself, like 1 minute introduction? Sure, okay. So let's see, just say, okay, your name, and then, which department, what year, and then, one cool things about you. Okay, for example, my cool things would be, I did skydiving before and I survived, okay? So let's start with, okay, so let's see. Yeah, one more thing is that, one thing I want to tell you guys is that I didn't do my undergrad in the US, okay? So sometimes I have some misunderstanding of how the undergrad system work here. Like if there's anything that you think, I'm assuming you guys know, but actually you don't, just tell me, okay? I think I've started to learn, how it works now, but sometimes I still get surprised, okay? So one more thing before we go into the class content is that I want to say a little bit of what we should expect, okay, for this semester. Okay, one thing is that probably some of you will come back to the ground in 2 weeks, but unfortunately, based on the recent news from UNC, also from Notre Dame and from other universities, realistically, it's very likely that the ground will be shut down at some point. Okay, just trying to be honest here. And it's always like, this is kind of situation like nobody wants, right? Like you guys don't want to sit in front of the computer to learn, and I don't want to talk to an empty basement. But you can always kind of, if you try to be the best be the best version of yourself in this tough situation, you always learn something, and that's actually college, right? The college is not about the knowledge, it's not just about making friends, but about knowing that you can be challenged, and then you can overcome those challenges, and then when you later are in your career, you repeat that again and again, and then become a successful person in your career, okay? And the other thing is that, well, for our class, it will be fully online, okay, unless we have a working vaccine, okay, and I don't expect that to happen, within 3 months. so that's about the COVID situation. And then one thing is that my family is actually quite tied with all this type of disease because my dad is a surgical doctor back in China. And then his hospital actually treated the very first SARS patient back in 2003. Okay, and then this year, unfortunately, my dad's hospital again was acquired to do a quarantine, okay, for close contact. So he stood by for 2 months in the hospital at that time. I always follow his advice in regarding whether we should go back to the classroom or stay here. And then so far, what I heard is that stay in your basement, okay. And okay, now let's get rid of this cartoon. Now let's start our class. Can you guys hear a little bit of noise from my mic? No? Okay, because someone is doing the mooring outside. Okay. So this class is called Quantum for Engineers. And then the reason to use this name other than quantum mechanics is because the content of this class is very different from traditional quantum mechanics. Because traditional quantum mechanics, you will learn like angular momentum, you will learn how particles collide, you will learn scattering matrix, and all of those are geared towards physics, physics majors. And I think at this stage of quantum technology, like quantum information, quantum computing, it's actually not necessary. It's not necessary to learn those things. Okay, we can just cover the basic concept and then actually jump into the quantum technology, like the teleportation, how you transfer a state from place A to place B without actually transporting that particle, and also like quantum key distribution, how to do 100% secure communication. And I think all of those things are actually more closely related to our engineering majors. And so here, okay, the first half of this class would introduce the basic concept and mathematical skills of quantum mechanics. Okay, so the first half is, the first few weeks might be a little bit, I'll say, you might be challenged intellectually a little bit, because what you will see, especially in this first class, I'm going to use a thought experiment to show you guys, is that quantum mechanics is fundamentally different from classical mechanics. Whatever you think or whatever you've learned in classical mechanics, if you try to apply that directly to quantum mechanics, usually you're wrong. Okay, usually you're wrong. And we'll show that very, very clearly in just a few minutes. Okay, so and first part is fundamental concept and mathematical skills, and then second part is the introduction of quantum technology. Okay, and the way I try to think about this class, especially for the engineering student, is that learning this class is actually an investment in yourself, just in case that in the near future, okay, before you retire, quantum computer become a reality, right? And then you don't want to be the one to be cut by your company, right? So you can at that time say, okay, I learned a little bit of quantum mechanics 20 years ago, and then probably I can contribute a little bit. And just on this point is that right now we have 17 students enrolled in this class, and the UVA bar to get a half TA is 20 students. Okay, so if you know any friends that are hesitating about taking this class or not, you can kind of try to convince them to whether they want to join this class or not, because then we'll have a TA, right? Then the class will be much easier for both of us, right? Okay. So now let's start the class. So one thing about the quantum mechanics, okay, a little bit of history is that it's established in the early 20th centuries. And then it's actually, if you kind of think about the most important scientific achievement in the past century, you kind of have to include quantum mechanics there. Okay, there are quite a few others. For example, one is the special and general relativity from Albert Einstein, right? That's kind of I don't understand that, but I think that's cool. Okay, and the second is probably the discovery of DNA, right? That's people learn how we can pass our genes from one generation to another generation, and how actually evolution work, right? Explain the entire that's the foundation of how we understand life now. And the third one, actually, I would put it is quantum mechanics. The reason is that quantum mechanics is actually the backbone of all the modern technology. For example, the semiconductor you guys use, semiconductor has to have band gap, and band gap is coming from the fact that electron is a wave. And electron is a wave come from quantum mechanics. Okay, and then we have electronics and the internet and also all these things. Anything that actually based on modern electronics, you can trace back the foundation, trace back to quantum mechanics. Okay, and then one thing that people don't really talk about is that, while this is kind of irrelevant, is that when you compare quantum mechanics to general relativity and also to DNA, right? If you think about it, the amount of impact on our daily life, quantum mechanics actually have way more than the other two. For example, general relativity. How much of you know one application that we're using from general relativity other than atomic bomb? Well, we're not using that, but that's one thing you can use. One thing is actually GPS. Okay, GPS, probably you guys don't know that GPS, the satellite, send a signal to your cell phone, and then there's a timestamp there. And by comparing the time difference, you know the distance between you and the satellite. But because the satellite is so far away from us, so far away from the Earth, it actually has to, the time on the satellite actually has to be corrected according to general relativity. Okay, and that small correction is actually important. If you don't do that, you will be missed by a few miles. Okay, so that's actually the only one application I can think of for general relativity. And then DNA, right now there's actually not much, right? Because the bioengineering is still mostly in the lab phase, and then probably in the next 50 years we'll see a lot of more progress. Okay, so quantum mechanics. What have you guys heard of quantum mechanics? Please, someone unmute the mic. I've been talking to myself for 20 minutes. Anyone hear about anything? Anyone know anything about quantum mechanics?
I learned a little bit about it in high school.
Mm-hmm. Can you name a few things about quantum mechanics?
Maybe the thing that I understood the best was light being a wave and a particle.
The particle-wave duality. Yeah. Okay. And then the other thing that I think a lot of you must have heard of is the uncertainty principle, right? Uncertainty principle. Anyone want to give a try to explain what uncertainty principle is? William?
Yeah. Isn't it with electrons that, the more you determine where they are positionally, the less you can tell about where they're going directionally, and vice versa? So if you're determining, say, how fast they're moving, you can't really determine where they are.
Yeah, exactly. Yeah. We actually, the first semester, we actually have, by the end of the semester, we have a t-shirt for everyone. So the first year, the t-shirt is someone driving, a driver is pulled over by a police, and the police asks you, okay, do you know how fast you drive? The driver answered no, because I know where I am. Okay, so it's kind of the using the uncertainty principle to get away from a bill, to get away from a ticket. Okay, and the other thing that you guys might heard of is the Schrodinger's cat. Right, that's why we had a cat here. I shouldn't erase it. Okay, the Schrodinger's cat. Does anyone want to give a try? What Schrodinger cat is? Andy, I see you unmute your mic.
Yeah, I was going to say, I don't know anything about Schrodinger's cat, but I was going to mention that isn't quantum, physics, I guess, related to the simulation theory.
Yeah, we'll talk about that a little bit. So yeah, so one takeaway from the particle wave duality, the uncertainty principle, and Schrodinger's cat. One takeaway is that quantum mechanics. The hard part about quantum mechanics is that there's no one clear message about quantum mechanics compared with DNA, compared with general relativity, right? DNA, you can say, okay, that's a thing that passed the genetic information from generation to generation. General relativity, you can say that, okay, if you have more acceleration or if you have more gravity, the time is slower. But for quantum mechanics, the information is more like the information that we give out to the public looks like more mystery than answering questions, right? So so here I want to show you, okay, why things will get worse and worse, okay, if we try to explain what they are, okay? And that's why we need one entire semester to learn about quantum mechanics other than just watching a 5 minutes YouTube video, okay? So let's start with Schrodinger's cat, okay? Wait a second. My apology. So let's start with Schrodinger's cat, okay? The reason we're talking about Schrodinger's cat is just to give you an idea of what quantum mechanics look like, why sometimes people don't like it, okay? Schrodinger's cat is that it's a thought experiment proposed by Schrodinger, right? One of the founders of quantum mechanics. And what he says is that, well, first of all, Schrodinger is a cat person, otherwise it would be Schrodinger's dog, okay? So what Schrodinger says is that, okay, there's a cat, one of his cat. Let's say he trapped it inside a box. Okay, trap a cat inside a box. And then next to a box, well, inside this box, there's a bottle of poison gas. Okay, or you can think about it as coronavirus. Okay, there's a bottle of coronavirus. Actually, coronavirus can infect cat. Okay, something that you guys should be aware of. And then next to that box is another box that has an atom. What the atom can do is that it can decay and then emit, let's say, a gamma radiation that break the bottle and release the gas. Okay, if it does that, then the gas will toxicate the cat and the cat will die. Okay, and the thought experiment is that suppose we wait for 1 hour and then open this box to check the cat. Okay, if you wait for an hour, okay, if you do this experiment many times, you will see that, okay, there are 50% chance that the cat is alive, 50% chance the cat is dead. And the question is, okay, the question that get Schrodinger's cat interesting is that what is a cat before you open the box? Okay, is a cat live or is a cat dead? Okay, so classically what we think about is that whether the cat is live or dead doesn't depend on us, right? Whether we open the box or not, okay, at a certain moment, the atom decay and then break the glass and then poison the cat, right? That will happen regardless whether you open the box or not. But one thing cool about quantum mechanics, or very confusing about quantum mechanics, is that in quantum mechanics, this thing is completely determined by you. Okay? When you open the box, you did observation of the atom. And then the atom will collapse into either radiate, 50% radiate, or 50% not radiate. Okay? If it radiate, then it kills a cat. If it doesn't radiate, it don't kill the cat. And before that, the cat, what we call is live in a superposition between life and death. Okay, between life and death. And this is something that we'll learn a little bit about in a little bit later. But then this is the whole idea of Schrodinger's cat. And the point here, okay, the point here, if you feel confusing, okay, that's normal. Okay, that's normal. If you already get what I'm talking about, then you're a genius. Okay, so it's fine to feel confused. And then let me point out why Schrodinger's cat. Why people discuss about Schrodinger's cat. There are two things. If you accept the idea that what the atom do, well, whether the atom emit the radiation or not, will not happen until the moment you open the box, then what it says is that whether the cat is life or death, depending on whether we observe the system, right? Depending on whether we open the box or not. And you think that's fine because it's a cat, right? But think about it. Think about it a little bit deeper. What if we are the cat and someone is watching us, putting us in a box called universe, okay? And then when they open it, 50% of us will die, and if they don't open it, we can continue to live, right? So the idea of our observation would decide what the atom do, and then would decide the life of the cat is kind of really counterintuitive, and it doesn't feel right as a living thing, right? And the second thing that's troubling about this Schrodinger's cat is that before opening the box, what quantum mechanics tell you is that, okay, the cat is actually both in life and death. Okay, it's simultaneously life and death. And imagine you're the cat, right? And you must be super confused, okay? You must be super confused, not sure what you are right now. And then this is one of the, that's why Schrodinger proposes, is to, what he actually want to do is that he want to point out some of the counterintuitive thing in quantum mechanics, and then try to trigger people to discuss the true meaning behind quantum mechanics. Okay, and if you really think about it, then that's one problem of talking to an empty room. I forgot what I want to talk about. Okay, my apology. Okay. Oh yeah. So trying to answer this Schrodinger's cat problem, right? The cat is both life and death. Some scientists create a concept many of you might heard of, especially if you watch the Big Bang Theory, is the multi-universe theory, right? The multi-universe theory says that, okay, when you create this scenario, the cat split into two, or the universe split into two, okay? One of them, when you observe, will die. The other one will continue to live. And these two universes never crosstalk to each other, so that you will never know. So the one in one universe will never see the other one in another universe. Okay, so that's kind of an elegant way to explain the superposition, the both life and death. But if you ask me, then my answer is always the same: is that because this theory has assumed that these two universes can talk to each other, right? So if we're in this universe, how do we know other universes exist? There's nothing you can observe, right? So your theory basically saying that you can't prove it and you can't disprove it, right? So this is not science, this is religion, right? You believe in something if you think it's true, right? So okay, so this is Schrodinger's cat. And uncertainty principle, well, we try not to, we'll talk about that later, but I think the Avenger talked a little bit about uncertainty principle, right? How the Ant-Man goes into the back, and then using the uncertainty principle is that when your energy, well, it actually makes a little bit sense that when delta E, well, what it says is delta E, delta T must be larger than something. I think the unit is wrong here. It's probably H bar, yeah. Then if you're very certain about your energy, then you're very uncertain about your time, right? And then the time actually can go backwards for a short period of time. And of course, something that's not really scientific about, the theme in the Avenger is that because this is uncertainty, actually you can't control it. If you control it, then you know it, right? So that's violation of uncertainty principle. But anyway, I mean, this kind of movie I really like. how they try to justify something really unreasonable with fancy scientific term and make it look like okay, unless you really know the subject. Okay, now let's start with the thought experiment that to highlight the difference between quantum mechanics and classical mechanics. And if you're not shocked, then with the result of this thought experiment, then well, you'll be a great engineer, right? Because you're willing to work with anything you see. Okay, so consider this experiment. You guys are all electrical engineer or computer engineer. Anyway, you deal with electron, right? You deal with electron. Now we know electron has many properties, right? It could be where they are, how fast they travel, and some of you might know electron also have spin, right? Like spinning up, spinning down, spinning left, right. So electron have many properties, and let's not make things complicated. So let's assume that electron has two types of property that we care about. Two properties that we care about. One is color. Okay, and let's say electron has two types of color. Well, we will make it binary just to make things simple, right? So the color of the electron can be either black or white, right? You can imagine this, okay, this could be the spin of the electron, spin up, spin down. I'm just using color as a representation. Okay. And then another property of the electron, let's assume its orientation. Orientation meaning, for example, like if you flip the coin, you have head and tail, right? Head and tail. You can think about it as electron on the left, electron on the right. Okay, they are all the same. A binary property, two of them, two pairs of them. Okay. Now, if this is, and now let's create something called electron pool or electron bank, right? Bunch of electron here. Well, the shape doesn't look good. Okay. And let's say this electron bank or electron pool is completely random. It's completely random. What that means is that if you pick one electron from it and you measure the color, then it will be 50% chance you're getting a black one and 50% chance you get a white one. Okay. If you measure orientation, then it's 50% head, 50% tail. Okay. And this is called randomness, right? So, and for classical mechanics, okay, this system is like super easy, right? You can classify this electron into four categories. One is that the color is black, and then the orientation is head. And the other one is color is black, orientation is tail. And color is white, orientation is head, color is white, orientation is tail, right? Very simple. And then because it's completely random, we know that all of them are 25% chance. And so if you use this electron to do any classical experiment, you can always know the result by referring to these probabilities, right? Okay. Any questions up to this point? Okay, good. Now let's try to define what we're going to do here. We're creating a measurement device to determine the color and determine the orientation. One we call it as a color box. One is called a color box, C, okay? And when the electron come in, the black one will pass, and then the white one will make a turn. Okay, that's a color box. So this way you can distinguish the color of the electron, right? By seeing whether the electron goes straight or whether the electron go up. Right? And then for the orientation, it's the same thing. We can build a orientation box. And the head one goes through, and then the tail one goes up, right? So these are the two ways that we measure, okay, the color and the orientation of the electron. Now let's imagine this. Imagine this. Imagine now you have this electron bank, electron pool, and then you start to send electron into this box, right? So classically, we know that 50% of the electron will go through, 50% of the electron will go up because of the, because it's completely random, right? 50% black, 50% white. Okay. So what about in quantum mechanics case? Any guess what would be the percentage of electron going through and electron going up? Any random guess? Well, I can start to call names.
I would guess 50-50.
50-50, right? That's a reasonable guess. Okay, and then up to this point, you're correct. Okay, 50-50, it's that simple. Okay, and then so it's the same for the orientation box, right? You have head and tail. 50-50. Okay. Now, I assume everyone remember this 25%, so I will erase here. Now imagine this. Imagine this. If I want to select an electron that is black and head, what would you do? You would send the electron from the pool, and then send the electron from the pool, and then first pass through a color box. Okay, black goes through, white makes the turn, and then I will attach the orientation box next to it, right? And this is tail, this is head. And based on classical statistic, we know that whatever goes through here, okay, would be black and head, right? Black and head, very simple, okay? And in quantum mechanics, well, the same thing, okay? In quantum mechanics, let's say the experimentalist want to double check things, They want to really confirm that the electron coming out from here is black and head. So they want to measure the color again. Okay, they want to measure the color again. And this is black, this is white. Now my question is this 100% black? So well, I see someone shaking your head. Andrew, is that you?
Yeah, I just feel like that's the point you're trying to get at. I feel like that's, I don't really understand why per se, but like from what I know, that will also be 50-50.
Huh.
I don't know why.
Huh. Well, you're actually the first one to guess it right. Okay. So from common sense, okay, we would say it's 100% black, right? Because whatever coming out from this path is electron that's black and head. It's black and head. But if you really do this measurement in quantum mechanics using electron, what will happen is that you will see 50% of the electron turns its color to white, and 50% of the electron remain black. Okay, remain black. And imagine, well, try to search for your knowledge stored in your head and think about if there's anything in classical statistics that can explain this. Okay, and it's the same thing if you go through this white port, then you go orientation, then you will also get 50% of the white one turn black, right? So it doesn't really matter. And anyone want to kind of guess what's happened here? Like make a reasonable guess what's going on here?
So the electrons are already black in heads, but they can still change color at the third color box.
So you think the color box changed the color?
Or it has the potential to.
Mm-hmm. Any other guess? I mean, because if I want to make a device that measure color, I wouldn't want it to change the color, right?
Yeah, I don't think. I think there's not just one electron. There can't just be one electron going into that last input.
That's a great point, and that was actually the question raised by a lot of scientists in the early age of quantum mechanics. Is that whether the electron interaction, okay, if you send a lot of electron there, whether the electron interaction changed the result. And later, when the technology evolved, people have the capability of sending electron one by one, right? Having one electron reach to this point and then send the other one to make sure there's no interaction. And then the result is the same, okay? The result stays the same, 50-50. So interaction between electrons doesn't really matter, okay? Any other guess?
Did the orientation box change the color?
Yeah, that's a great point. So if we assume color box measurement won't change color, right? And then there's no electron interaction between each other, then possibly this orientation box change the color, right? It might be something that you measure in the orientation and then accidentally change the color. It could be this could be the suspect, okay? This could be the suspect. Now, so of course you can have the assumption, right? Whatever orientation box does, it changes the color to 50-50. Okay, completely mess up the color. And then scientists again think, okay, is that really the case? And then they do the second experiment. You see the scientists sometimes are really annoying, right? They keep poking things. And the worst part is that they're having fun by doing this. Okay, so the second experiment they're trying to do here is to, okay, make this quite similar. Okay, you have a color box, and then black goes through, have orientation box, and then now you have a head and then a tail. Okay, and the thought is that, okay, if we move the color box to here, you also see 50-50 because the orientation box mess up with the color, right? So now how about we combine these two paths together? Right, let's say we can do that. Let's say we can have really good control of the electron. This part 50% black, 50% white. And this part is also 50-50 of black and white. And then we combine them, and then we measure the color again. Okay, we measure the color again. And what is the reasonable guess of the color here? You're combining two streams of electron. Each one of them is 50% black, 50% white. And then you combine these two pools of electron together, what would be the color of the electron?
So 50% black and white?
50% black and white? Okay. If that's a result, it would be great, right? Because we preserve the classical mechanics and only have to assume that the orientation box has something wrong, right? Does everyone agree with this? Okay, and if this is the case, then well, the class can end here. Okay, I have no more to teach you. The reality is that if you really do this experiment,
Is it 25%?
oh, that's a great guess, but it's no. But that's a great guess. I have seen multiple students making that guess, and well, it's usually good, right? You divide that by half, and then you try to do it again. The next one is 12.5%. The reality here is that the white one is 0%, and then the black one is 100%. Okay? Does that make sense? No, right? It doesn't make sense. If you think it makes sense, you're wrong, right? So we have assumed that the color box don't change color, right? That's a measurement device. It shouldn't change any color. And then now we have this path have black and white, half and half. This path have black and white, half and half. And now you combine them, magically the white electron disappear or were turned into black. And there's actually nothing in between here, right? Coming out, there's only one color box that won't change the color. Okay, so that's really, really weird, and that doesn't make any sense, right? And if you think about it, okay, you say, okay, maybe we can go back to to that argument. Maybe you have multiple electrons, and then they have interaction here, and then that change the color. And people again can do this experiment by sending only one electron at a time, and then they still see this effect. Okay, 0% white and 100% black. Okay, they still see that effect. And using this setup, what you can even do is say, okay, you say, I don't know, I really want to see what will happen, and so I block this path, right? I block this path. And then if you take a look, when you block this path, it's just the previous one, right? The head and black go through, and then measuring the color. And if you block this, then this result will become 50 and 50. Again, doesn't make any sense, right? The electron going through here, whether it changed color or not, why does it matter about the electron going this way? All right, it simply doesn't make any sense. And that's actually the key point. Okay, we have very simple explanation for this, and we'll reach that in a few minutes. But that's a lot of this experiment is actually the key point of why we need quantum mechanics. There are many microscopic behavior of electron, of light, of nuclear. You can't explain this phenomenon with classical mechanics. You simply can't. Okay, there's no way you can do that. And people tried, and they tried it for 20 years. At the time that when people first saw quantum effect, somewhere at the end of, I think it's 1890s, all the way until the quantum mechanics was established, it's in the middle of 1920s. So it roughly is 20 to 30 years. And these things really, confuse people. And what we're trying to do in this class is trying to compress that all into one semester of learning, and hopefully you guys can understand. And now let's come back and see how we can explain all these things with very simple concept that we change what it requires that the change of way that we think about electron. Okay, so the first one, how the orientation box change the color. Okay, this is exactly the uncertainty principle that we talk about. Okay, uncertainty principle. So when the electron come here, you know its color, right? After that, you know its color. And then after here, you know its orientation. So when you know its orientation, 100%, right? 100% of electron going out from orientation box is head. When you know this information 100% accurate, then you know nothing about its color, right? So that's why the orientation box will turn the color into 50% and 50%, okay? This is uncertainty principle, and we'll actually explain this in detail, okay, where does uncertainty principle come from and how you can actually derive it. The second thing is a little bit more complicated, okay? If you think about it, the key problem here is where do the white electron go? Right, you have 50% white here, 50% white here. When you combine them, they disappear. Where do they go? Okay, and if I tell you guys that you actually have seen this in high school, hopefully you're not shocked, but you guys all know Young's double slit experiment, right? Okay, so what that experiment is that, let's see here, okay. You have a light coming in from the first slit, then make it a point source of the light. And then on the second part, you have two slits, okay? Two slits that create two point source, and then you have a screen to receive this light, okay? And the result of this, the result of each individual source is that, okay, if you have one source, then it light up this area. If you have this, the bottom part, it light up, also light up this area. But when you have these two combined, then you start to see interference pattern. Okay, interference pattern, that's the Young double slit experiment. It's a very key experiment that that prove that light is a wave. Right? Now, how is that connecting to here? How is that connecting to here? If you take a look, is that in the Young double slit experiment, there's certain part that is completely dark, right? They're completely dark. But does that make sense? If you think about it, the first source, it has light coming to here, right? The second source also have light coming to here. So when you have both sources illuminating this spot, why does the screen is dark? Okay, where are the photon goes? Okay. And the key point here is that these are waves, and waves can be described as, for example, the first one arriving here is E1, E cosine, if there's a length L1, K L1, right? K is a wave vector, KL1. And then the second one, well, there's a path L2, and it's plus E cosine KL2. Okay, and you know that from Young double slit experiment, or from simple cosine and sine, you know that at some certain place, cosine, this cosine can be the opposite of this cosine, and they two can cancel each other. Okay, that's the interference of wave. When you have interference of wave, two bright spots can create one dark spot. Okay, so this is exactly the same thing as we have in quantum mechanics here. You can have 50% white coming here, 50% white coming here, but when they combine, if your interference is destructive, then this white electron, will get cancelled. And mathematically, the way to express this is that the white electron coming on the top part is a wave, but with a negative sign, and then this part would be a wave, but with a positive sign. So when you combine them, they two actually cancel each other. So if you want to translate this wave interference pattern to here, okay, mathematically that's what you would do. Okay. Any questions?
I have a question.
Yes.
So you said like it's have a negative y and positive y, so that's the reason why they cancel off each other.
Mm-hmm.
Right, so how about if they have negative black and positive black?
Mm-hmm.
So why is not 100% y and 0% black?
Yeah, that's a very good point. So the question is, okay, why don't the black one cancel each other, right? Why the white one cancel each other? And the part has to do with that initially the electron is black here, okay? So then the orientation box will do something funny. When you combine them, you preserve the black one. The way to understand this is that think about this, think about why it turned 50%, 50%. The reason it turned 50%, 50% is because if you measure the orientation here, 100% hat, then you know nothing about the color, right? So the color becomes random. But in this path, when you're doing the measurement here, do we actually know the orientation? No, right? We let both orientation go through. So when you're looking at here, there's no way you can tell the orientation. So we didn't measure anything of the orientation. So if the orientation is not measured, then it will not change the original color. So that's why the color here come out is 100% black. So you can do this same experiment if you use this port, okay? The color box going down, and then you go through orientation box, and then combine them, and then measure the color again here, okay? And if you do this, then this result will be 100% white, right? Because again, the reason is that the orientation, because we're combining them, so we actually don't know anything about the orientation. So we're not violating the uncertainty principle. Whatever color you have in your electron, you're preserving that. Okay, does that make sense?
I have a question.
Yes.
So like in probability, if this was a probability equation, the outcomes here that you have given wouldn't be the same, right? Because those are constant, but in this case, you're comparing it to the uncertainty principle with waves. So at every point in the path, it's never constant, 0%, 50%, or 100%. It's always changing.
So I get your question here. So the key difference here is that the wave itself, if you think about the wave, okay, the light wave here, we're actually not measuring the electrical wave, right? We're measuring the intensity of the light. So what is the intensity of light? Is actually the square root of your wave, right? So that's the key difference here. When you're having a probability, the probability can only go from 0 to 1. But when you're having a wave, you can go from -1 to 1 because it's not the probability until you square it, right? So having the ability to go from cosine have negative components. Having the ability to be a wave and create a negative components, and then later square it become the probability is the key that why you can combine 50-50 and then you get 0. So it's not about probability, it's actually about the wave, okay? Yeah.
Thanks.
Yeah. Other questions? Okay, so so that's the key takeaway of this class, well, of this today's lecture, is that while there's uncertainty principle, although we really haven't go into details about this, and the second one is probably more important, is that from this moment on, everything is wave. Okay, you are a wave, and you will be asked to calculate your wavelength, and that's actually a homework, and we are going to answer that question. Very interesting question is that, think about the wave is that the reason that you can, the reason that, well, you can have Wi-Fi in your room while the router is in the other room is that the wave can penetrate the wall, right? And if you're the wave, why can't you penetrate the wall? So we'll answer that in roughly 1 or 2 weeks with the homework set. And that's all about today. And then if you have friends that hesitate about this class, ask them to join. That's the way we get one more TA. Okay. And I will stay here for 5 more minutes. And then if you have any questions, you can ask about it. Okay. Thank you, everyone.
I just want to say I made a group mate for the class, and I posted the link in the chat for people who
Oh,
haven't joined yet. So.
okay. Yeah, thank you.
Okay, thanks. Is there any way with the boxes to arrange it such that you negate the color? So that you actually change it so it's 100% black. So it comes out one box and it says it's 100% white, and then after a couple more boxes where you observe things, it comes out 100% black.
Can you repeat the question? I didn't quite get it.
I mean, I don't think it's actually possible. So, like, you see like how it says like the color comes out and it comes out black,
Yeah.
and then you have it come out through some other boxes. Is there any way, like, so at the very end it comes out a box and it's 100% black?
Let me think about it. So I think what you're asking is that can you reset the color to black, right?
Yeah, like, can you invert it?
Yeah. That's doable. Let me think about it. That's called, in quantum mechanics, that's called preparing the state. So you don't have to prepare it in completely random. You can actually, if you measure it's white, then you can apply an operation to turn its color. Okay? And then when you measure it's black, then you do nothing. And that way you can convert everything into black. Yeah, that's of course doable and then necessary for anything. If you want to make a computer, then of course you need to prepare the initial state, right? If you want a black, you can have a black.
And you could you do with just those boxes you have there, just the color box?
No. These boxes are measurement box, and then to do that you need a gate operation box, and we'll discuss that in 2 months. Yeah.
Thank you.
I have a question. How often will we the homework sets?
Oh yeah, it would be weekly homework.
Is there one due this week?
No, the first one would be next Thursday.
Okay, and those will be due like at midnight?
Yeah, I probably should say that. So usually it would be, I will give you guys 2 weekends to finish the homework. Okay, so I would say it would be like if we release next Tuesday or next Wednesday, then it would be the Tuesday in 2 weeks.
Okay.
Yeah. And then the final homework would be do it like in a week. Otherwise, it would be like into the final week. Yeah.
Okay. Thank you.
Professor?
Yeah.
I just enrolled in the class this morning, and I wasn't put on I don't have the collab, or it's not on my collab, and I didn't have an invitation for this Zoom meeting, so
Okay.
I was asking her also. So I was just curious, 1, how I could get on the collab page, and then 2, I missed the first 10 minutes of class, so I was curious.
Yeah. So you can send me an email. Okay, you can Google my name, UVA, and then there will be an email. Send me an email. I will add you in the collab. And then second is the class will be posted on YouTube next morning, so that you can rewatch the first 10 minutes.
Okay.
Yeah.
Great, thanks.